Hello, welcome to the section 1, video 4, Deep Learning Hello World. Here we are going to train a deep neural network with Keras. In this video, we are going to take a look at the MNIST dataset of handwritten digits, which is the most basic dataset studied in deep learning. After that, we are going to train a deep convolutional neural network to classify images of handwritten digits. This is to give you a taste of what we can do, but don't worry if you don't understand all the details. We are going to go back to everything later. Just pay attention to the reasoning. Here is all the instructions to set up our environment. We are basically using Anaconda distribution and these versions of Theano and Keras. You can also use them to make sure that you can reproduce all the results with the same environment that I used. So let's move into the IPython notebook. Here, I have an IPython notebook loaded up using the environment that we just saw how to set up. Notice that in this first cell, we have the imports of all the libraries that we will need for this example. Pay special attention to the types of layers that we're going to use, which are the dense layer and the convolutional layer. The dataset that we are using is the MNIST dataset, and we will use Keras itself to load the dataset for us. Here I'm using Keras with Theano backend in a GPU. In this second cell, we load the MNIST dataset and reshape it to the format that our network is expecting. For example, we have only 10 classes from digits that go from 0 to 9, and each image is a 28 by 28 pixels image. We use load data from the MNIST module to load our input images and their corresponding labels for both training and test dataset. We resize the images to have each image in a row with only one channel since they are grayscale images and the 28 by 28 pixels. We rescale them to be between 0 and 1. We convert the labels to the one-hot encoding format that basically says what is the probability of that input image belonging to each class. In this code here, we visualize the first 9 examples from that dataset. And they look like this: handwritten digits, 28 by 28 pixels. Our goal is to define a model that gets these images as input and outputs the probability of it belonging to one of those 10 classes. The model that we are going to use here is a slightly modified version of the LNETS 5 originally proposed by Jan LeCun. It is a 5-layer deep neural network with 3 convolutional layers, followed up by 2 fully connected layers. Here's how to define this model using Keras. We start by instantiating a sequential model that stacks all the layers that we're going to use. To add layers to the sequential model, we use model.add. For reference, here's the API of a convolutional layer. A convolutional layer expects the number of filters of that layer and the size of each filter. If the convolutional layer is the first layer of the sequential model, we also have to define the input shape of the images that this model will get. From the second layer to the last one, Keras infers the input shapes for the layers. Our first layer here is convolutional with 6 filters, each one of 5 by 5. Again, our input image has only one channel and 28 by 28 pixels. After the convolutional layer, we add a nonlinearity and a max pooling layer. The nonlinearity for this case is the ReLU, the rectified linear unity. The max pooling will get the maximum value from pool sizes of 2 by 2 pixels. The next layers follow the same reasoning. But this time, we will have 16 filters and 120. We use the same nonlinearity and the same max pooling. Dropout is to increase regularization and performance on the test set. After the convolutional layer, we flatten the image and add our fully connected layers. The first fully connected layers has 84 neurons and the same nonlinearity. The last one has 10 neurons, 10 output neurons, one for each class, and a softmax nonlinearity that rescales the sum of the outputs to 1, so we can interpret the output of the network as a probability over the classes. To train our model, we have to first compile the graph that we just defined here. We compile that with the model.compile function. The inputs of the model.compile function is a cost function or a loss function that defines how well the network is doing comparing the output and the desired labels, and an optimizer that calculates how the parameters will be updated to decrease the loss. Let's run this cell to compile our model. After the model is compiled, we can use model.fit to train the model. Fit expects the following parameters: the input images, their corresponding labels, a batch size, which is the number of samples that the network sees at once, and the number of epochs, which is the number of times that we will run through the entire dataset. The validation dataset is just for us to see how well the network is doing. They are not used to update the parameters of the network. Running this is kind of fast for me because I'm using a GPU. If you're using a CPU, it may be a little bit slower. Here, after only 2 passes through the entire dataset, only a few seconds, we obtained almost 99% accuracy on the test set. In this last cell, we visualize a few results on the held out test dataset. The network does a pretty good job, even in a few complicated images like this 5 in here. And this ends our coding section. And in this section, we learned what is deep learning. After that, we saw a few open source libraries to do deep learning with Python. And finally, in this last video, we did some coding in our first Hello World deep learning example with the MNIST dataset. And then in the next section, we will start going into details of how things work behind the scenes with backpropagation and Theano for the rescue.